Welcome to Pod 4 Journal Club, where we break down some really fascinating new research. Today, we're diving into a paper that asks a huge question in AI. Does size really matter?
Okay, so take a look at this. What's so wild here is that you've got this tiny AI model, QED-Nano, with just 4 billion parameters, and it's going toe-to-toe with absolute giants on some of the world's toughest math problems. I mean, the results are almost identical, even though there's this enormous size difference. It's kind of nuts.
This performance, it honestly seems almost impossible, right? It's like the AI version of a featherweight boxer jumping in the ring with a heavyweight champ and actually landing some serious hits. So that brings us to the central mystery we're going to unpack today. How on earth did the researchers pull this off?
All right, so to solve this mystery, let's first get a handle on the challenge they were facing. We're talking about AI's big problem with high-level math.
You see, the world of top-tier AI is pretty much run by these massive proprietary models. And you can think of them like black boxes. Yeah, they're super powerful, but how they're trained is a total secret. They cost a fortune to run, and most researchers can't get their hands on them. And that, right there, creates a huge bottleneck that really slows down progress for everybody else.
So, the secret sauce for this little model's big power, it isn't just throwing more data or more computers at the problem. Nope, it's all about the training method. The researchers came up with this really clever 3-part recipe to make it so incredibly smart.
So here's how the recipe breaks down. First, they teach the model what a good proof even looks like. Then it gets to practice, but with an AI grader that gives it super detailed feedback. And for the final step, it learns this special trick for dealing with those long, really complex problems, so it doesn't lose its way.
Okay, stage 1 is basically an apprenticeship. QED-Nano gets to learn by copying a massive expert model, in this case, DeepSeek Math V2. It goes through thousands of its proofs, and the goal isn't just to get the right answer. It's about absorbing the style, the structure, that whole logical flow of what makes a perfect mathematical argument.
Then comes the practice phase. Now the model tries to solve problems all by itself and gets a grade. But here's the cool part. It's not just a simple pass/fail. It gets really detailed feedback from a rubric, kind of like a teacher's notes all over your homework, showing exactly where the logic was strong or where it went off the rails. This helps it learn from its mistakes with, just incredible precision.
And the final ingredient is something they call the reasoning cache. This is for those really complex marathon-length problems. The model actually learns to pause and summarize its own progress at each step. It's like leaving a trail of breadcrumbs on a long hike so it doesn't get totally lost in the weeds.
So, there you have it, the recipe. An apprenticeship, some tough graded practice, and a neat little memory aid. But did it actually work? Come on, let's look at the results.
And wow, the numbers are pretty staggering. By using a special process that gives it a little more thinking time, QED-Nano scored an incredible 57% on problems from the International Mathematical Olympiad. I mean, these are problems designed to stump the absolute brightest human minds on the planet.
And just to put that into perspective for you, a score like that means it completely blows past a lot of open models that are dozens of times bigger. It's just more proof that a smarter approach can absolutely beat brute force.
But this, right here, this is what's truly stunning. Look at this comparison. QED-Nano, at 4 billion parameters, is right up there, nearly matching the performance of the 685 billion parameter DeepSeek model, and even the super secret closed-source Gemini 3 Pro. For a model this small, that is a massive achievement.
The authors themselves put it perfectly. They say the key takeaway is that this shows a path forward for powerful, specialized AI that doesn't have to rely on these planet-sized models. It's solid proof that you really can work smarter, not just bigger.
But, of course, there's always a trade-off, isn't there? To hit that peak performance, the model needs more thinking time, using these special techniques called scaffolds. And while the performance goes way up, so does the computational cost. I mean, the best method they use cranked up the token cost by more than 21 times. So it's not exactly free.
Okay, but no research is perfect, right? And what I love is that the authors were super upfront about the current limitations of their approach. You always want to see that.
So, 2 main challenges really stood out. First, that initial apprenticeship training, it can make the model, a little too wordy. They actually call it a length explosion, which is pretty descriptive. And second, the model has a habit of using brute force computation instead of finding those elegant, really clever shortcuts, those aha moments that are the hallmark of human genius. So, what does this all mean for the future of AI? This, to me, is where things get really, really exciting.
When you get right down to it, this work is basically a blueprint for a totally different future for AI. A future where progress isn't just about who can build the biggest, most expensive model. This kind of approach could really democratize the field, you know? It could let smaller, more focused teams build some seriously powerful, specialized AI.
So what's next? Well, future work is definitely going to focus on refining this whole training process to make the model, a little less chatty. But the really juicy challenge, the big one, is figuring out how to teach an AI to have those genuine, creative aha moments, the kind of insight that we value so much in human problem solving.
And that kind of leaves us with this big, provocative question, doesn't it? Are we heading for a future that's dominated by just a few giant, all-powerful AI brains? Or will the future look more like a vibrant ecosystem of lots of smaller, specialized experts all working together? What this research suggests is that the second path isn't just possible, it might be incredibly powerful.